Microfluidics focuses on the control and manipulation of small fluid volumes within microscale channels. At this scale, fluids behave differently than in larger volumes due to phenomena like laminar flow, where fluid layers move parallel without turbulence, and capillary forces, which dominate over gravity. Fluid dynamics and microfluidics also exploit properties like electrokinetic flow, which uses electric fields to control charged particles in fluid, enhancing precision in fluid handling. Microfluidic devices in medical diagnostics use blood or saliva samples and separate specific components like proteins or glucose for precise detection of diseases at an early stage, using tiny volumes that minimize patient discomfort. Microfluidic channels can be compared to a complex network of tiny roads in a city, where cars, fluid particles, move smoothly along designated paths with minimal interference. Just as city traffic flows efficiently when cars follow designated lanes, fluids in microchannels maintain orderly, predictable paths, allowing scientists to control them with remarkable accuracy. Sensors within microfluidic systems detect chemical or biological changes by measuring variations in properties like pH, temperature, or conductivity. These sensors use mechanisms such as electrochemical sensing, where chemical reactions generate electric current, optical sensing, where light interactions reveal chemical properties, and piezoelectric sensing, where mechanical stress from fluid movement generates voltage. In diabetic care, a wearable patch with a glucose sensor uses microfluidics to draw and analyze interstitial fluid, which reflects blood glucose levels without invasive blood sampling. This integration enables constant monitoring, sending real-time alerts when glucose levels deviate from the normal range. Think of this integration like a smartwatch's heart rate monitor, which continuously records your pulse and alerts you to abnormalities. In wearable microfluidic devices, sensors perform continuous surveillance on body fluids, detecting subtle changes in biomarkers that may indicate health issues long before symptoms arise. Sweat is rich in electrolytes and metabolites, making it an ideal, non-invasive fluid for health monitoring. Wearable sweat sensors in microfluidic patches can track biomarkers like sodium, potassium, glucose, lactate, and cortisol, offering insights into hydration levels, metabolic stress, and hormonal fluctuations. Wearable sweat patches help athletes monitor dehydration by tracking sodium and potassium loss during intense physical activity. By identifying real-time hydration needs, athletes can make informed decisions about fluid intake, avoiding fatigue and optimizing performance. Similar to a fuel gauge in a car, which signals when refueling is necessary, a sweat monitoring patch informs users when electrolyte levels drop. Just as a low fuel gauge warns of potential breakdown, low electrolyte readings warn of impending dehydration or metabolic stress. Continuous glucose monitoring, or CGM, devices use microfluidics to analyze glucose levels from interstitial fluid, which is a close proxy for blood glucose. These devices use a microscale needle or capillary to draw minute amounts of fluid. Then, an electrochemical sensor quantifies glucose by measuring the current generated by glucose oxidizing reactions. A CGM system sends glucose readings to a smartphone app every few minutes, providing trend analysis that helps diabetic patients maintain optimal glucose control. Users can see glucose patterns, detect spikes from meals, and adjust insulin accordingly. Imagine CGMs as autopilot systems in cars. Just as autopilot constantly monitors speed and direction, adjusting as needed, CGMs continuously check glucose levels, helping diabetics steer their glucose levels within safe ranges without frequent manual checks. In microfluidic devices, controlling fluid movement without pumps is crucial. Capillary action, which is fluid movement driven by adhesion and cohesion. Electroosmotic flow, which is fluid flow driven by electric fields. And surface tension, which maintains fluid boundaries, are all fundamental. These forces allow precise fluid transport and mixing in confined microchannels, making microfluidics ideal for wearables that rely on passive movement. A microfluidic skin patch for wound care may use capillary action to transport wound exudate to a sensor, which monitors infection markers without external power sources. This process resembles how a sponge absorbs water. Small pores within the sponge draw water up through capillary action. Similarly, microfluidic devices use their tiny channels to draw and guide fluids efficiently, just as nature uses capillary action in plants to transport water from roots to leaves. Blood-based wearables face challenges, such as preventing coagulation in small channels, avoiding contamination, and ensuring accurate microvolume handling. Innovations like microcoatings with anticoagulant properties, precise microvalves, and hydrophobic barriers prevent issues like clogging or fluid loss in blood analysis microfluidics. A microfluidic wearable for anemia screening uses specialized coatings that prevent blood clotting, capturing a tiny blood sample and testing it for hemoglobin levels to detect anemia early. This is like carefully adding honey to a narrow straw. Without the right conditions, honey can clog or stick, halting flow. Similarly, blood in microfluidic channels needs specific treatments to flow smoothly, making it viable for accurate biomarker testing in minuscule amounts. Electrochemical sensing translates biochemical changes into readable electrical signals. When a target molecule interacts with the sensor, it triggers a reaction that releases or consumes electrons, creating a current. Microfluidic systems often use amperometric, potentiometric, or conductometric sensors for real-time biochemical analysis. Wearables for monitoring lactic acid during exercise use electrochemical sensors to detect changes in lactate levels, allowing athletes to gauge fatigue and adjust intensity to avoid muscle strain. Think of this like a small electric switch. When fluid containing a target molecule touches the sensor, it flips the switch, creating a readable signal. Just as turning on a switch completes an electrical circuit, biochemical interactions complete the reaction circuit, signaling specific chemical changes. For wearable devices to operate independently, power efficiency is crucial. Energy harvesting techniques like thermoelectric, which generates power from body heat, and piezoelectric materials, which produce energy from movement, are now integrated into microfluidics to power wearables without bulky batteries. Wearable patches that monitor body temperature and hydration use body heat to power sensors, making them self-sustaining. This is especially valuable in extreme environments like military training or outdoor sports. This is similar to solar-powered calculators that rely on ambient light to function autonomously. In wearable microfluidics, energy harvesting captures body-generated resources like heat or motion, powering the device without needing an external battery. Wireless transmission in wearable microfluidics uses Bluetooth low energy and near-field communication to send data with minimal power. By connecting to smartphones, wearables provide real-time health data through apps, alerting users and healthcare providers to critical health metrics. Wearable sweat sensors transmit pH and electrolyte data to a smartphone app, warning users if hydration or pH levels are off balance. Such data can inform users when to rehydrate or seek medical attention if prolonged imbalance is detected. This is like a weather station that collects and sends weather data to your phone. Similarly, wearable microfluidics collects health data and transmits it, enabling real-time tracking and timely response to health changes. Real-world applications illustrate the power of microfluidics in wearable health. From detecting dehydration, heart conditions, and even certain infections, these devices are proving essential in settings where continuous health data can impact patient care, including hospital sports and remote health monitoring. Discuss the success of wearable ECG patches for heart patients. These patches monitor electrical heart activity continuously, alerting patients to irregularities that may require immediate intervention, potentially saving lives in high-risk populations. Think of these devices as health radar systems, continuously scanning the body for signals of distress, much like radar systems detect approaching storms. This continuous data allows early intervention, making health monitoring as proactive as weather forecasting. Integrating microfluidics into textiles is advancing quickly, with fabrics now embedded with microchannels and sensors that can detect health conditions by interacting with skin or sweat. Smart fabrics can perform diagnostics directly from the body, potentially aiding in conditions like chronic illness management or infection detection. Research is underway to create hospital gowns embedded with microfluidic networks to monitor biomarkers like pH and blood oxygen, providing continuous diagnostics in a non-invasive manner. Imagine these textiles as having an embedded healthcare team in the fabric itself. Just as a GPS map shows where you are in real time, smart fabrics with microfluidics track health markers, continuously updating patients and caregivers on health conditions. Wearable health monitoring raises concerns about data privacy, security, and consent, particularly with continuous monitoring. Additionally, reliance on wearables may shift responsibility from healthcare providers to users, potentially increasing stress and misinterpretation of data. To mitigate privacy concerns, glucose monitoring devices now encrypt data to ensure it is accessible only to authorized users, protecting personal health information from unauthorized access. Like security cameras that monitor without sharing images publicly, health wearables must ensure data remains private, accessible only to those authorized. Just as we expect cameras to respect privacy, we expect wearables to guard sensitive health information.